Hey everyone, my name's Natasha, and today I'm going to be continuing where we left off last time in R Programming Basics Part 1. In that video, we covered the fundamentals of objects, data classes, and also did some rudimentary data manipulation. If you haven't seen Part 1 yet, or you just want to review, I've linked it down in the description below. In this video, we're going to be applying those skills to working with larger data sets, and also tackling some more practical real-world examples. We're going to cover unloading external data, installing and using packages, some new subsetting techniques, and plotting our results if we get to it. Alright, let's get started. Go ahead and open up RStudio. You can see that I've already navigated into my directory and I made a new script. It'll be important that you know exactly what file path your script is saved to because we're going to be unloading some external data in a sec. So I think I briefly mentioned what packages are last time. They're basically just collections of functions that have been assembled and published by programmers in the R community. The main package we're going to be working with today is called Tidyverse, and Tidyverse is especially cool because it's actually a collection of packages. Two of the most important ones that come with it are dplyr and ggplot2. dplyr was built for data wrangling, so it is insanely clutch when it comes to manipulating and subsetting data with precision. ggplot2 is a plotting tool, as you probably guessed. It lets you generate a huge variety of graphs to represent your data. Pretty much anything from scatter plots and histograms to contour maps and bivariate distributions. It also gives you a massive range of customization options, so you can make your plots look exactly as you need them to. Okay, so to install Tidyverse, use the command install.packages with the name of the package in quotes. So install.packages, Tidyverse, and Control-Enter. In the console, you should see a bunch of lines sort of spam generating, and then it should say package Tidyverse successfully unpacked. This might take a sec, so just be patient. Then, to load that package into your working script, you would use the library command, so library Tidyverse. The second package we're going to check out is the janitor package. This one was built for beginners, so it does have a pretty limited catalog of functions. But I'd still argue that it's one of the most effective toolboxes for cleaning data in a simple way. I'm going to go ahead and install and load Janitor the same way we did with Tidyverse. If you get a warning message like this after loading anything, it usually means that either the package or your version of R is just slightly out of date. 9 times out of 10, you can just ignore it. R will continue to work perfectly fine. Now that that's sorted, I'm going to show you a method for loading external data into your workspace. It works by accessing a file directly from a source URL and then storing it in the same folder that you're working from. Pretty simple. If you scroll down to the description, there should be a Google Drive link to a spreadsheet on COVID-19 data. Now, we're going to type the command download.file, parentheses, URL equals, and then copy and paste down our URL. And then we say dest file equals, in quotes, the destination that we want to send it to. That dest file function just serves to give R a destination folder to send the new download to. In my case, my working directory is called R tutorials, so that's where I chose to send it. Then you can make a new object to store the data in. We could call it something simple, like COVID data, and then just type the command read CSV to save the file as a CSV type, and then assign it the value of the data that you just downloaded. Alternatively, you could download the file directly from the link as you normally would, drag it into the correct folder on your computer, and access it the same way using that read CSV command. Now, if you look up in the environment window, you'll see an object called COVID data that has 216 observations of 18 variables. In the console, we can figure out what structural type that object is with the class command. So just class parentheses COVID data, and it tells you that it's a data frame, or more specifically, a data table. The reason why we assign the data to a CSV is really just to make it more readable for us. See, this file down here called R tutorials is where we sent the downloaded URL data with that dest file command earlier. If we click on it to open it up, it is just a jumbled mess of raw data. There's no columns or rows or pretty much any organization at all. But now that we've read that nonsense into a CSV, we can just type view COVID data and it opens up the table in RStudio's data viewer. Super neat, very easy to work with. If we want just a brief snippet of the dataset, we can use the head function, which, if you guys remember, just outputs the first 6 rows in the console. And before we make any alterations, we could use the structure function, notated as str, and that'll just give us a brief structural overview of the dataset. Or you could use the glimpse function, which will give you an information-dense summary of the data in your table, laid out in row format. Okay, sick. Let's start subsetting. dplyr gives us this magical new tool called the select command, which lets you choose all of the columns that you want to retain in a new subset. So say we want to make a new dataset with only the vaccination data. We would make a new object called COVID subset 1, and then assign it with select, the name of our dataset, and then the variables that have to do with vaccination. So total vaccinations, people vaccinated, and people fully vaccinated. Then we can see how it looks with that view function again. We could also use select to exclude certain columns using that minus sign operator. So if we want to retain every variable except for stuff regarding age, we could say COVID subset 2, use select to assign it, and then subtract median age 65 or older, and age 70 or older. And then we can see how it came out in the data viewer. Scroll to the right, and all of the age columns have been successfully dropped. There's a bunch more keywords called helper functions that work in tandem to give that select function just a little more utility. Right after you list out your desired dataset to work with, you just add the helper functions like this. Contains will let you select all variables that contain a given character string in their name. So you could select all variables that contain the letter T, or the word the. Starts with will let you select all variables that begin with a given character string, and ends with will perform the opposite. The colon operator lets you select all the columns in a range between 2 variables, including those bounds. There's a few more helper functions, but most of those work with specific naming conventions or expression types, so I'll just leave those for some other time. If we want to subset rows based on certain conditions or criteria, we could use the filter function. So, for example, we could make a new subset that contains only the countries that have more than 1 million total cases. And as you can see, the number of rows just dropped from 216 countries to only 37. We could then make our filter even more specific and add a condition to parse out all the countries with a population below 50 million people. And then look at that, our subset gets even narrower. Or you could use the double equal operator. You could use it to subset only the countries from South America if you wanted. Okay, cool. But what if you wanted to select and filter data simultaneously? There's a few different approaches you could take to accomplish this. The first one would be to make a temporary data frame that you apply the filter function to, and then you would take that temporary object to work with instead of the original data when you call the select function in a follow-up line. But this can get super clumsy to work with, not to mention the fact that you basically have to keep track of double the amount of unique names and objects. The second method involves nesting functions. So for example, let's try to make a subset that includes the total number of COVID tests and the rate of positive results, and then we filter through those selected columns to only retain the rows that correlate with Asian countries. We can nest the filter command within the select command and then list out the variables that we want right afterwards. Okay, so that worked fairly well. It's also interesting to note what just happened. The order of columns in our subset will align with whatever order we requested them in. So if I list the total tests first, then it shows up as the first column in our dataset. Or if I switch its position with positive rate, then that change would also get translated over. Nesting isn't necessarily incorrect or bad form to use, but it does limit the readability of our code because it just crams everything onto one line. And if you needed to execute a more complicated set of parameters, it can be pretty difficult to follow just because of all of those parentheses. The best way, in my opinion, to perform multiple functions at the same time is through another dplyr feature called pipes. Pipes use this little snippet of syntax that's just a % symbol, a right vector bracket, and another % symbol, and they work like this. You declare your new subset, assign it the value of your original data, or whatever data you're working with, add a little pipe operator, move on to the next line and add a new line of code for each select or filter or whatever operation you want to perform. You would follow up each line with a pipe until you get to the last one. And once you view it, you'll see that subset 6 is literally identical to subset 5, which we achieved through nesting. But personally, I find the piped method to be a lot cleaner, since you can actually see each operation working on its own line, but maybe that's just me. You can think of pipes in R as working kind of similarly to pipes in Mario. You jump in one end, and the pipe connects a continuous path together until you pop out the other end. Alright, so now that we've gone over subsetting data, let's talk about some easy ways to manipulate and transform it. The mutate function is basically used to add new variables to your dataset, but it could also be used to alter existing variables. So if you needed to scale your data by a certain metric or perform a unit conversion, mutate is what you would use. So let's say we wanted to make a new data frame based on our original data, where the rate of positive test results is expressed as a percentage rather than a decimal. We could use mutate to take in our original dataset, create a new variable called %positive or %pos, and then assign it the value of positive rate multiplied by 100. Okay, when you open this in the data viewer, you'll notice that the positive rate column is still there, and the % variable that we just made got appended, or just tacked on, to the end of the dataset. If we wanted to drop that old positive rate column entirely, we would just have to set its value equal to null, and then that'll force R to void its value. If we wanted to perform a similar operation, but we didn't want to retain any of the other variables in our data, we could use the transmute function. So we just put in all the same parameters, same syntax and everything, and then it only outputs our new variable. If you really wanted to use transmute, but you still wanted to keep a few of the other variables in your subset, you could just list them out before you define the new column, like so. We can combine all the skills we've covered so far to perform some pretty elaborate combinations of operations. We can start by defining a new data frame. Assign it the value of our original dataset and add a pipe. If we look back at our data, we can see that there's actually a bunch of missing values scattered throughout, and all of them are notated as NA. We could remove those values from certain variables using the is.na command and the filter function. So we can just say filter, ! which means not or exclude, is.na, and then total tests or some variable, followed by a pipe. We could add another filter criteria if we wanted, and only subset the data from Europe. Then let's go ahead and select all of the variables we want to retain. Let's go with the country, the total number of cases, the total number of tests, and the positive rate. If we really wanted, we could integrate that same mutate function from earlier and add a line to convert that positive rate into % values and then drop the original column. Okay, I'm going to make that our final line, so we don't need to add a pipe indicator on that one. We can view our new subset and, okay, there you go. Actually, there's still an NA value in our %positive column, so we can go back into our script and add in one more filter command to get rid of that. Okay, cool, it's gone. I know I said I was going to cover plotting in this video, but it's getting pretty long and I really don't want you guys to get bored, so I'm going to wind down here. But part 3 will be up shortly to pick up where we left off. If you have any questions, suggestions, or requests for future videos, don't hesitate to leave a comment and I'll reply as soon as I can. Feel free to leave a like and subscribe if you want. No pressure though, and I'll see you all next time.